One of the interesting connections that we can now make is the connection between the magnetic flux and the electric field. So we know that an electric current produces a magnetic field. And we know that a uh, a magnetic, actually should say a changing magnetic flux will induce a current, and when we have a current, then we we know that a current also gives us an electric field. Right? So an electric field can be used to move charges, but a current is going to create an electric field, and that electric field then becomes connected to the change in the magnetic flux. Now let's see how this happens. So we have the voltage potential between 2 points, A, B, is equal to the integral from A to B of the electric field dot product of the line differential length, and the induced potential can be related to the potential due to the electric field and the induced potential is just negative n times the derivative of the change in phi with respect to time. And if I put everything together, transitive property, then I have that the integral from A to B of E vector dot dl vector is equal to Faraday's law. I don't know what I wrote here. Just saw that. It's not what I meant to write. Looking at two different things. Okay. So I can write that over here. So the consequence is that with the connection of these two, we remember that this line integral means that the path must be closed around a magnetic field. Because this path is going to be related to our area for our loop. And we must remember that this relationship is not conservative. And if we have no moving charges, then no changing magnetic field. And no changing magnetic field, then no moving charges. So we're going to talk about this consequence more in chapter 31, but since we're talking about Faraday's law, the connection with Faraday's law, it's good to review it at this point.